Hi Paimarats, welcome to a new project which has a simple goal, and that is to play with the question of how big is a water molecule and what does it actually mean. When you search the internet, the standard answer goes along the following lines. You calculate total number of molecules in 1 liter of water, let's say. You divide the volume of 1 liter by number of molecules. You get the volume of one water molecule. The above way of thinking, however, hides from you some amazing facts, which is exactly the topic of this project. But first we need to learn and understand the difference between van der Waals and covalent radius of an atom. For that, I drew a little sketch here of a water molecule. The small covalent radius measures the extent of nucleus and electron cloud in space. However, the electrons which are surrounding the nucleus are electrically charged, right? So if you try to bring another water molecule close by, the two will start repelling each other. And the limit of how close you can bring them is roughly the van der Waals distance. So that's the bigger one here. And that van der Waals volume delineates the effective space of the molecule, even if the space is actually empty. And that is the center of today's question. If we compare the physical extent of water molecule by calculating its volume with our covalent radius and compare it with the effective one, how much empty space are we going to find? The sketch shows the oxygen and hydrogen atoms with the covalent and van der Waals volumes in scale, so you clearly see some kind of a difference. And in order to compare our calculations to reality, we first need to find out the number of molecules in 1 liter of water. For that, we are going to use molecular weight of water and Avogadro constant. If this sounds like a magic to you, I have another interesting water project called P in the Sea, where I exactly explain these kind of things, so have a look. The next step is calculate volume of one water molecule. We simply sum volumes of three spheres representing one oxygen and two hydrogen atoms. We start with van der Waals radii, and after we get volume of single water molecule, we multiply by number of molecules in 1 liter of water, and we expect that the result will be somewhere close to 1, meaning 1 liter. And indeed it is. It is 0.97. This simply means that using van der Waals radii, we explained almost 98% of water volume. So it is truly a good measure of effective water volume. After that, we switch to covalent radii, which are somewhat smaller, right? And we repeat exactly the same steps. We calculate the volume of one and then multiply by total number of molecules in 1 liter. But the amazing result is that this explains only 4% of water volume, which also means that basically 95% of the space inside the water is totally empty. If you think that the water is some kind of special case, you can repeat exactly the same calculations also for a brick of pure gold. The result will be not so stunning, but still gold is around 50% empty. The conclusion is that the matter is very holy, and typical calculations you learn in school or find on the internet keep it hidden from you. It partially makes sense, because we cannot take much advantage of that empty space inside the water. We cannot squeeze the molecules more or put anything else there, because the repulsion forces are so strong. As an extension of the project, you can calculate how much empty space is actually inside the covalent volume of the water. If we assign radii to protons, neutrons and electrons, count them, sum their volumes and compare it to our covalent volume result, I guarantee you'll find much more empty space there too. Good job, and try it yourself by opening either the task or the solution notebooks, which are linked in the video description. Until next time, bye bye.